we're going to have now the last talk within the session, which will be delivered by Tarja Knuuttila and Johannes Jäger. I know both of them well. They're actually colleagues of mine in the department. Tarja is a professor of philosophy of science at the University of Vienna, and she leads the Possible Life project, which is on synthetic biology. And Yogi is a project leader of a project about agency and organisms. And yeah, please come here, and we're excited to hear your talk. Thank you.
Let's go both. So, hello and hi. We are changing gears here entirely, so we are talking about more general things and philosophical things and really going partially away from science, but at the same time actually going back to science with Yogi. So this is a collaboration between a philosopher of science and then an evolutionary biologist who has become more and more philosophical during the last years. So let me see, where can I? Oh. So is this?
You're good.
Here. Okay, yep. So then we started to think about this talk in terms of the title of this conference, and so to think about the different meanings of interface and then interfacing. And obviously, like the usual meaning is like for the user interface is this user interface that we come across when we basically deal with computers, through which we can then communicate with the computer, but actually, eventually, this allows us to communicate with other users and technologies behind the computer. And then there is another sense in which one could think about interface, and that would be like that of interfacing. And we know that interfacing obviously is used in many different senses, more scientific and less scientific, but here we were interested in thinking about interfacing actually as a sewing kind of metaphor. So think about like garments and the layers of textile that are used in the unseen side of garment, but typically to reinforce the garment. So the idea is there, and this was a PhD thesis on social media, that like this interfacing would be something really intimate, very close, but at the same time, it's still an additional layer, but it's reinforcing the connection. And so when then we think about convergence, so are we thinking about convergence in terms of this kind of interfacing where you still have this interface, even though it's really not very well seen, but still very important? Or are we thinking about that maybe like as some kind of convergence, strong convergence in terms of assimilation, perhaps, of the human and the digital? And so our question is, I mean, is some kind of radical assimilation perhaps taking place, perhaps in the future? Or is this even something that is not possible at all? Can it even take place? So in order to ask this question, then we consulted different fields of inquiry. So basically, what's at stake here is the relationship between humans and technology. And so first we thought about cognitive sciences. And if you think about cognitive sciences, obviously, like all these computational approaches seem to promise some kind of strong convergence, because we can think of both artificial systems and then natural systems as some kind of systems that compute. At the same time, there are other approaches in terms of various kinds of interfacings. So I'm here talking about these familiar 4E approaches to cognitive science, in which then cognition is thought about as extended. So it's not just like the cognition would be something within our heads, but it's extended into artifacts that we use. Or then we can think about also cognition as distributed between the artifacts and technologies and humans, also embedded in various kinds of situations. as well as enacted by various kinds of embodied actors. Now, if they then go to philosophy of technology and STS, so typically both science and technology studies, I'm talking about STS, and it's basically referring to science and technology studies. So what they really underline is the non-neutrality of technology and also the non-linear nature of technological development. And so the idea there is that we really don't know when a technology is going to stabilize and like what are the results of this stabilization and what's going to be then the effect of different kinds of technologies for our practices. And some very important, I would say, stream of thinking within science and technology studies is actor network theory. And the idea there is that actually, like when we think about technologies, we should think about assemblages of non-human and human actors. And it's not that they would basically converge in any way, but they work together in networks, and this would have very unforeseen consequences, often like a disruptive potential. And also, like what's happening there is that new connections are being built, new goals are basically conceived. Something new is happening that wasn't like predicted on the basis of like, well, I would say the ideas on which then these technologies were basically developed. So there is the possibility of disruption, much more that of disruption than any kind of neat convergence. And so in addition to these frameworks coming from cognitive science and science and technology studies and philosophy of technology, we thought that we could also have a view from biology. And now here I'm giving over to Yogi.
Thank you, Tarja. Which way is this going? Okay, perfect.
Yeah.
Okay, thanks. So when we talk about convergence, what I was missing so far in the meeting is when we talk about intelligence as well, a comparison between the origin of the word intelligence, which is in a human context, in a biological context, and what we talk about when we talk about intelligence in AI. And I think, and actually the founders of the field debated this very intensively in the 1950s already, the field should not be called AI, but algorithmic mimicry, to make really clear what we're doing here. So we are not trying to reproduce the organization of a living system and its intelligence. We're not even trying to reproduce what we think about intelligence is in organisms, but we're trying to mimic intelligent behavior through computational systems. Okay, and that should be made explicit, because otherwise we misunderstand what this technology is, what it can do for us, but also what its dangers are, very fundamentally, because we get into the danger of confusing the living and the digital. And so I'm going to take a huge step back. This is an argument that is made in this paper that's on arXiv already. I'll just give you a very quick overview, but let's take a very big step back at this point of the conference and just, I have to show you, this is a machine, okay? It's a computer. It's built according to a von Neumann architecture, which is an imperfect sort of approximation to a universal Turing machine, and it has certain design features. One feature is that it's designed to run as many different algorithms as possible, okay? So there's a maximum separation of the software and the hardware side by design, okay? Now this is not a machine, very clearly, okay? It has a completely different organization than the computer. And the main feature of that organization is that it makes itself. Okay, so that's called autopoiesis. This is Greek for self-making. It's self-manufacturing. That means it can make all its components. Think of a cell that is producing all its macromolecular components, proteins, DNA, membranes, and everything. But not only that, it can also self-assemble. So it puts those together in a way in which the cell as a process completes a life cycle and reproduces. Reproducing is not just copying. It's much more complicated than that. There's overlap between the parent and the offspring generation, and it's reproducing an entire organization of the cell, not just the DNA. Okay? So the metabolism that's in your cells right now has been going on since the very origin of life. I always think that's an awesome thing to think about. That's very different. Your computer, I always tell students, okay, if you randomly change a connection in your laptop, do you think it's going to improve its performance? Nope, never. But random mutations in animals can do that. What this self-manufacturing organization gives you is autonomy from your environment. It was Viktor Frankl who said, between perception and action lies freedom, and this is what animals have, what machines don't have. Computers are pure input-output processing machines. No matter how many billion parameters your large language model has, all it does is complicated input-output processing. This is not complex, it's complicated. No matter how many million parameters you have, you will never get consciousness emerging from that thing. I tell you why in a minute. So the second thing is embodiment. That's very important. I told you before, the computer is designed to have maximal separation of software and hardware because you want to run as many different algorithms as possible on the computer. If there's any software in your body, it's maybe the genes, coding for proteins, other coding schemes. In an organism, there is no distinction. Software is hardware. There's maximal integration. This is an argument that Howard Patia already made in the 1970s and nobody read it. But there's a fundamental difference between how computers are designed and how organisms are organized. And that difference is extremely important because you will not be able to build a self-manufacturing system with the kind of design we have in computers. And also, if you put that computer in a moving set of hardware, robot, it's still maximally separated, the software and the hardware, okay? Fundamentally different. Even if the robots dance and look like humans, they are not anything like human beings at all. And this is very important. So your algorithmic system always lives in a small world. This is a term that's been introduced by Leonard Savage in the 1950s. A small world is a world in which every single problem you encounter is well defined. Okay? It lives within a specific computational architecture. It's been programmed in a specific language. Its data are formatted in a certain way. The algorithm will never encounter any ill-defined problems, which means it's stuck in one frame. This is called the frame problem in AI. It's been around for 80 years. We have made absolutely no progress because algorithms never encounter the frame problem. But as a human being, you live in a large world. You get up in the morning and you're confused, okay? You look around. Almost all of your problems are not well defined. You have to define your problems before you can actually solve them. And now if you define intelligence simply by problem solving and optimization, which most people in the AI world do, that's not intelligence, okay? And I would recommend those people to get out into the large world a little more instead of sitting in front of their computers. Okay, so what is intelligence? If we talk about artificial intelligence, general intelligence, we need to think about natural general intelligence first. And I'm using this very nice definition by Reuterblatt. Here are the components. So to be intelligent as a natural being, you need to be able to reason and solve problems. That AI can do. You need to be able to learn. AI can do that too. You need to make inferences, logical thinking. AI can do that too. You need to have common sense. AI can never do that because that requires a uniquely human perspective. And not only that, a localized, grounded perspective in your local environment. That's evolved, that's historically contingent, all of that. You need to be able to autonomously define and adjust goals. That you can only do if you're self-manufacturing. The goals of a computer and algorithm, no matter how indirect, are programmed by a programmer who is a living agent. You have to be able to deal with ambiguity in ill-defined situations. Algorithms, by definition, cannot do that. And you have to be able to create new representations of knowledge, framing your problems, okay? Algorithms, as I told you before, can't do that. So to be a living being requires you to be able to solve the frame problem, the problem of relevance. So you need to be able to pick out what is relevant to you in this situation from a large world, okay? That's a fundamental difference between you and a machine. So this means
living beings are characterized, and this is the topic of my research project at the moment, by natural agency. And here's a definition. A living agent can be defined as a self-constructed unity that by actively regulating its exchanges, that engages with the world, sorry, the projector is really not that good. A self-constructed unity that engages the world by actively regulating its exchanges with it for adaptive purposes that are meant to serve its continued viability. Here's an example. Organisms can act on their own behalf in pursuit of their own intrinsic goals. Algorithms cannot do that. They don't have intrinsic goals. And they will not ever have those, no matter how indirect, how much of a general range of target functions you program into your AI. It'll be programmed by you. Okay, to summarize, here's the difference between machines and organisms. The goals of a machine are imposed by an external agent, the programmer, the designer. The organism sets its own intrinsic goal, either by evolution or by developing by behavior. Most components of computers are made in Taiwan. My cat, self-manufactured. And so these systems that are stuck in a small world are entirely formalizable in the sense of defining problems. Okay, so this is Hilbert's original technical definition of what a formal system is, while organisms in this sense of Hilbert are not formalizable. They are engaged in defining problems, so they are engaged in the process of formalizing. Okay? Symbolic aspects isolated, so because of this maximum separation of hardware and software, you can run simulations on your computer that are not physically accurate, like every evolutionary simulation of biological evolution that's ever been done on a computer. Okay? It's not physically accurate, while the symbolic aspects are directly embedded and embodied in an organism. We do not have a model of the organization of an autopoietic organism that is consistent with the second law of thermodynamics at this point. I'm not saying that there isn't such, I'm here and giving this talk, so I'm proof, because I think I'm compatible with the second law of thermodynamics, that this is possible. But we have no explanation for it. So there's a gap between biology and physics here that needs to be filled, that we haven't filled yet. That would be very helpful to understand all of these questions. And with that, I give you for the...
Okay, I mean, just some
the conclusions. Basically.
Yes. So we think that, there is probably no hope of any strong convergence between the digital and the living, but this doesn't mean that there could be many interesting interfacings and new kind of developments, as we have heard already today, really important. This is not at all to deny the importance of AI research and all these kinds of areas of research that lie in between biosciences and engineering sciences, physics and chemistry and so on. I mean, this is not the claim like that. It's simply that we think that maybe in many of these discussions, the characteristics of life haven't been enough thought in order then to actually advance any arguments concerning how then life and technology, life and cognition and natural cognition and then artificial intelligence could really converge. So that's one of our points, and we think that AI is potentially, we see that already, a very disruptive technology, and it's very difficult to forecast the influences of AI now for human-machine engagements, and in this regard, science and technology studies are really an important area of research. So not just thinking about all these fancy things that we actually can accomplish, but they are going to have repercussions at everyday life, also at the university setting. We are for the moment now thinking at our department, how are we going to deal with the fact that the students are using ChatGPT? Who knows, what's the situation after 5 years? How much we would actually need to change our teaching and the way in which we then basically set up our applications or then our exams and so on. So all these technologies are potentially so disruptive. And so then finally, this is an addition of Yogi here. He added a singularity is extremely unlikely, and maybe you should be explaining it. So yeah, the point is that AI will not replace human intelligence anytime soon. I mean, we are not, of course, saying that that's not impossible, but somehow, yeah, not anytime soon. And maybe you would like to say something about this singularity.
Right, yeah, no, the point is just that in the current algorithmic frame of AI research, we are not going to build a machine that is going to want to take over the world, because we cannot build a machine that wants anything. Machines don't want anything. So machines only want what we program into them. So it's up to us, and what we see in society is much more that we give our agency freely to machines that have no agency, rather than the machines will be taking over. So the real danger here, and the discussion also that I think Joanna brought out really, really well, is that this is more or less a design problem. I have that from Joanna, so I should acknowledge her, that we should design those systems so they can be used as tools, and that we don't get fooled and give our agency away to the technology that we have created.